Hi, and welcome to the last class for Introduction to Astronomy. We've delved into different topics of what constitutes or makes up astronomy. We've talked about where we are in the universe, going through things like what are galaxies, what exists in our solar system. And today I thought it would be really good for us to end on something that kind of mixes with astronomy, but also just the world around us, and that's light. So I will bring up our thing for today. But first, I just wanted to ask and pose a question for you to really ponder while we're here. What is it that we already know about light? So we know that when it's light out, when there's day, we know that things are bright and we can see things that have different colors. Like I'm looking outside right now and it's a beautiful day and there's light coming in from my window. And, you know, light can show us where things are, but light is actually a little bit more than that. So I thought there'd be something really cool for us to try before we really delve into the class today. Something that I found is really cool. It's from Phetnet. And I love this tool. I love it so much. I've actually played with it a few times. And as you get into more physics-related things, this will be a really useful tool to be able to practice optics, which is a branch of physics that deals with light. But so what we have here is just an ordinary beam of light that's coming out of, say, a flashlight. And it appears white. And so we're going to see what happens when we play with it. So let me just put it here so that we can see more about that. So these are different types of prisms. Prisms are usually pieces of glass or something that is clear, and they have different angles in them, and it will interact with the light and different things happen from it. So I thought we could try that. So here you're seeing like this white beam of light is being bounced through. We call this refracting, where it is being bent and it comes out the other end of this triangle, and you start to see that it's being spread, and there's a rainbow. So the rainbow that we see, red, orange, yellow, green, blue, purple, or violet, we call this Roy G. Biv as an acronym. This actually is only a small portion of light that we know and are aware of. So as we keep playing with this, if you bend it more, you'll see that some of it is has different ways, and that's really cool, where you can see that some of the different types of light are being bent more, and then so you have some separations of light. Not really important. This one is pretty cool. Trying to get it so that the angle is about right. Can't really get it. So this is actually a really fun thing to play with. You can see how light gets bent at different angles. This is a really good example of how white light, we call this white light because it appears white, is actually just the entire rainbow put together. And so all of the light that is in this, it appears white, but it's actually the whole rainbow. And so you can see actually a clear definition between red, yellow, green, and blue. But there are colors in between there. And then you can also see it like here. And there we go. right there. So I encourage you to play with this. This will be on the handout you have for class. This is really cool to play around and see like different types of light and some stuff that happens like that. And you can also play around with like different things like water. Well, I want this to be water. Give me water or give me death. So you'll see how things can be bent or reflected in different mediums, which we consider things that are different. So air will reflect and bend light differently than if it were going through air or glass. So that is something really cool to see. So that is a brief warm-up about what light is and what light can do, especially in prisms. So let us get started. And if I can pull up my presentation, there we go. So what we know about light is that it is this thing that we may not really know a lot about before we learned about what light is. So what is light? Light is actually a form of energy, part of this thing called electromagnetic radiation, and it travels and behaves like a wave. So we're actually going to talk a little bit about what a wave is, but we call this energy photons. And so photons move in this wave-like pattern, and they have energy, and they can move everywhere. So this light that's hitting my face and I'm blocking it with my hand, it means it's hitting my hand and it's not coming through to my face. The reason you can still see my face is because it's being reflected off these different surfaces all around me. And then it's hitting my face and it's hitting into the camera. And then you're taking that from your screen and the light is hitting your eyes. And you have these things in your eyes called cones and rods, and they take the information from the light that you're receiving, and it forms this image with color. So all light, all light, and it's not just visible light, all light travels in the form of waves at really fast speeds. We say it is 300,000 kilometers per second, or that is also 186,000 miles per second in a vacuum, which means there is no friction, which is when you are sliding on a carpet rather than wood, you feel like it's harder to do it. That's because of friction. So in a vacuum, there's nothing for light or anything to experience friction or any other sort of forces on them. So one vacuum you may be aware of beyond the vacuum that you use to clean is space. Space is a vacuum. So there are different types of light besides the light that you can see, which we call visible light. And this range of light that you can see, a scientists call it the electromagnetic radiation spectrum. So this has 7 different types of light, and we'll touch on what those are in a little bit. But first, what is this wave motion that I'm talking about? So waves are this motion. It goes up and down, and you can see this with water. That's why I included this image in the bottom right of water and how surfing works. It's wave basics. So you'll have a wave that moves like this. And so when you have a wave that looks like this, the top of my hand and theoretically where my elbow is, those would be the crests or the peaks of the wave. And then the bottom is, we call it a trough. And so this is a pattern that is made where it is the same, usually. the same distance between this middle point, which we call a reference line. So we look at the crests to the troughs, and we can usually cut them straight in half, and they'll have a reflection on the other side of this line, which we call the X and Y axis. So when we are measuring length of a wave, we are looking at this distance between each peak to another peak, or a crest if you prefer that, or a trough to a trough. So you'll see in the upper right-hand corner the definition of a wavelength as according to a crest to a crest. And we measure these lengths in some different ways, but really we just use this to talk about the differences between different types of light, because different types of light travel at different lengths of light, which is why we call them wavelengths, because their waves are different lengths. So each type of light has their own unique wavelength, and we can measure these wavelengths by looking at the distance between their two peaks or their two troughs. And you don't have to look at a whole wave, you can just take those two sections, and it's very easy to be able to measure a wave like that. We measure the height of a wave, and this is important because actually the length of a wave can tell you, how far it's traveling. But when you're looking at the height of the wave, in addition to the length of the wave, it can tell you how much energy is in a wave. So this height of a wave, we call this an amplitude. So it measures the height of a wave, and it is the measurement between the center or the reference line, or also we call it an equilibrium point, which means everything is equal and essentially it is zero. And the highest peak, or you can also use it to the lowest peak, but if you are measuring from the center to the trough, the value is negative, technically, so it is better to use a crest if you want to keep things positive. In astronomy, the amplitude of a light's wave is important because it tells you about the intensity or how bright a light is compared to other lights that have the same wavelength. So if you have a red, if you have something that's red, and the intensity of the redness is not as much as right. So this red is very red, but compared to this red, it is not so much. And we are not sponsored by Nintendo. It's just the only other red I had. It's because the intensity of the red on the logo for the Nintendo Switch is not as intense as the red that is on this cut up piece of Canadian red maple leaf. So that can tell us when we're looking into space, if we're looking at something with whatever type of light, it can tell us how much energy is coming out of that when comparing with the same type of light. So just to recap, a wavelength tells you, it can tell you the type of light, because every different type of light has its own wavelength. And then the amplitude can tell you the intensity or the brightness of that light. So what types of light are there? There are 7 different types of light. And as we just said, every type of light has its own wavelength. So in the spectrum, we do separate each of these 7 types by wavelength. and you can measure actually by looking at the spectrum. There's a difference in wavelength, and in the opposite direction there is a difference in energy. And we'll talk a little bit about that in 1 second. But when we measure these wavelengths, we sometimes use this tiny unit called an angstrom, and it's a Swedish the unit representation that we use is a Swedish A with a circle on it. Just so you can see it. Actually, do it like that. So it looks like that. And it's named after the Swedish man who discovered them, whose last name was Engström. So it's very small. It is scientifically notated. We use powers of 10. So it is 1 to the 10 negative 8 power, meaning it is 0.0000001 centimeters long. It's very small, very small. But when we refer to different types, it's just easier to use certain things like a meter, which is 3 feet, or a nanometer, which is an even smaller portion. Sometimes we use kilometers, which are about 1,000 meters. So when we talk about that in the rest of the presentation, just keep that in mind. So let's get started. The first that we're going to talk about are radio waves. Now, radio waves have the least amount of energy, but the least amount of frequency. So actually, let me bring this image up that I want to show you. So we'll do new share of this. So this is an example of the light spectrum, the electromagnetic spectrum. So we are looking at radio waves, and so it has a very low frequency of wavelengths, but it has a very long wavelength. So the amplitude and the wavelength it's just very long. And you'll see as it gets, to the other side, there is more frequency, but less distance between the peaks. We're going to do a new share, and we will go back to the presentation. So radio waves, as we just saw, have the least amount of energy, thus the smallest amount of frequency. They can be ranging in size from very long. So they can be over 100 kilometers long. That is definitely more than a mile, to really short. So they can be kind of down to a centimeter to a millimeter. So like the size of that, like the tip of my finger, to like even smaller than that. And they can actually be bent around mountains and follow the Earth's curve if they're really long. But if they're really small, they cannot do that, but they can be reflected off of the atmosphere on the Earth. So you'll see that there's different types of radio waves. Depending on the frequency range, people will use different types of frequencies to have different stations. So if you hear like, I don't really know the radio stations up here in Vermont, but in New Jersey, so you'll hear like 102.7 FM radio, or WBGO is 88.3 FM. Those are the different frequency ranges that are being used. And so they have the ability to hop onto that wavelength of the radio radio waves using radio waves. And that's how they can create radio stations, and that's how you'll be able to hear them, which is really cool. We have conquered radio waves. Next, we have microwaves. So if you haven't heard of a microwave before, you've probably heard about it in close to your home. Sorry. Microwaves are some things that we actually use in a microwave to cook food. So it's a form of radiation that's being used to cook your food in a specific way using photons to break up certain parts of your food using water. But yes, so they can range in size from a meter to a millimeter. So they do have that interaction with radio waves. So they're pretty close. They were actually called microwaves because they were, before we actually had microwave technology, microwaves were assumed to be radio waves, but they were so much smaller. So micro means much smaller. So that's why they were called microwaves, because they were smaller radio waves. Unfortunately, they are limited by visual horizons, meaning if you look out your window right in front of you and you can't see past a hill, if you're on a hill, that means that you can't see beyond it. And so microwaves are the same way. They cannot be reflected or bent like radio waves are, so they are much more limited. So if you have it's like why I cannot have a radio station to listen up here in my car to listen to WBGO from New Jersey. I can only listen to the things around here because they have their limits with traveling. Of course, you can listen to them online because they do have that capability. But if you were just using a radio, you know, you can have that ability, but microwaves do not. Next, we have infrared. Now, infrared is more common to know about thermal cameras, where you can see different levels of heat. Now, you can see that on the top image, where there's someone who is looking away, and you can see like where different parts of like heat are. So it looks like their face is cooler, and then like their neck is warmer, and they have like warmth here. That is actually telling us the temperature of someone's face. And so infrared waves move from about 1 millimeter to 700 nanometers. And now that's where you're getting to. It's very, very small. I encourage you, if you have a ruler, you'll see how small a millimeter is. So nanometers are much smaller. And 700 meters actually brings us into the visual light spectrum, which we'll get to in a second. Infrared is actually very important because it can reveal things to us that we may not necessarily be able to see with visible light. So looking at the Carina Nebula that is underneath the image of the person looking away, you'll see the Carina Nebula, and there are a bunch of stars and just like this big ball of gas. And we don't necessarily know if it's hot or cold, but using infrared, we're actually able to see that it is much cooler. And there are things that are inside that are much warmer, and those are stars that are being born. And so infrared can tell us about things like the centers of galaxies or nebula clouds that we may not necessarily be able to see because of physical objects that we can't see past. So light is really cool that allows us to kind of see beyond things. And that actually connects to other portions of the spectrum, which we'll see later. So visible light, as we were playing with in the beginning of this class with the prism, it is white light that encompasses all of the light that we can see, but yet it is still very small. So it is between the ultraviolet and the infrared regions of the electromagnetic spectrum. And so they're very small, and it goes whichever way that you're moving from the spectrum. It's either red, orange, yellow, green, blue, purple, indigo, or violet, indigo. Sorry, indigo, violet, or violet, indigo, blue, green, yellow, orange, red. Just depends. But as we talk about the rainbow, we do go from red to indigo. And you can see that it's very important that we talk about specific types of wavelengths, because different colors have different wavelengths. And that is really important to also have when you're looking at things using spectroscopy, where you aim a camera at an object, and you can get absorption or emission lines, which will tell you about like what colors are coming out of it using visible light. And it can tell you what objects are there, because certain elements like hydrogen or oxygen give off different colors. So that is also really useful. Next is ultraviolet. Now, you would have probably heard more about its acronym, not acronym, but the shortened word for it, UV. You call these UV rays, and it is from the violet indigo region of the visible light spectrum to about 10 nanometers in size. So very small to even smaller. There's a lot more energy because they are a lot closer to each other. So the reason why we have to go, when we go outside, you should always be wearing sunscreen. Sunscreen will protect your skin from being damaged by UV light, because it can actually damage these things in our bodies called DNA. And that is the genetic code that makes up all of our bodies, everything around us. And the energy can actually break it down and create burns, which is actually damage being made to your skin. I had a biology teacher who actually said, when you go out and tan, it's actually like you're putting yourself on a frying pan and turning yourself into bacon, because that's what you're doing to your skin when you sit out in the sun, especially if you don't protect it. So it has a lot more energy, particularly due to ionization, which is not really important, but I thought it'd be cool just to say that ionization is when the photons, what we talked about, which were the particles of light, they have these things called electrons. So electrons, neutrons, and protons make up atoms. And so when these photons have more energy, they can lose their electrons. And so there's like electrons floating around, but it creates this thing called ionization. And so it can be pretty dangerous to have that, at least on this energy level. But ionized salt is good for you. Don't worry about that. So this is an image of our sun using UV. Disregarding the flares of orange and red, the UV spectrum actually shows a picture to us in both green and blue. And so this is an overlapped image of those two photos taken by NASA. And so our sun, while it appears to us that it is yellow or orange, it actually isn't just that color. Just because we see it in the visible light spectrum like that doesn't mean it actually is the same color. So it's also green and blue. Next we have X-rays. Now X-rays are pretty popular well, not popular, they are commonly used in medicine. But first we'll say that they range in size from 10 nanometers. So you're recognizing a pattern here where one of them ends, one of the measurement ends for one section of light, it begins for another. So it ranges from 10 nanometers to 10 pictometers. Now pictometers are very, very small. That is about, 1 pictometer is 1/1,000,000th of a meter. I can't even begin to understand how small that is. It is tiny, 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 tiny. And they were called X-rays because actually the guy who discovered them in 1895 couldn't tell what type of radiation they were, so he called them X-rays. If you ever watch the show X-Files, it's because they were things that were unexplained and they couldn't put them into this organization file with everything else, so they had them labeled X. X-rays can be produced by electrons, but also in lightning. So if people you'll sometimes see in comics or animations where a character gets struck by lightning and you can see their bones and they go, ah, and you see their whole skeleton. That's because it contains X-rays. And they're commonly used in metal detectors if you're going through the airport, or if you have to put something through baggage claim. They'll actually use a small amount of X-rays, not harmful for you at all, to see if there's anything on your person that is metallic, because that can be dangerous, or whatever. They want to see what's in your bag to make sure you're not carrying anything dangerous or illegal to wherever you're going. But it's also used in medicine, because if you break a bone, it can show us where the break is, or to see how, if you have to get surgery and get an implant in, which are made of metal, you can see if it's gone in correctly and how your bone is healing or whatever you need it for. So it does have really good uses, but we do have to be careful with X-rays. X-rays can lead to actually just as much damage to your DNA or your genes as UV light is, if not more. So you have to be careful when you are being exposed to X-rays. That's why if you are getting an X-ray scan, you have to wear this gown or shield that is made of lead, because it can't get through that metal. So because of that energy, they have a lot more capability of causing damage. But you'll see on the pictures, I have some images of X-rays being done on bodies, but then we also use X-rays to look at different objects in space. So this, I believe the middle image is a shot of our galactic center of our galaxy. And so you'll see some of the stars, and then there's gas. And then on the bottom are 2 pulsars. And lastly, we have these things called gamma rays. Now, gamma rays are quite more used in research when you're talking about black holes, because gamma rays can come out of black holes. I'm not going to really go into that because that is some high level stuff. But essentially, they come from an atom decaying or falling apart at its center. It takes a lot of energy to do that, and so that's why it has the shortest wavelength and the highest energy. And essentially, there's no way to tell about the range of the size of these. Essentially, anything that is smaller than 10 picometers, which is the end of X-rays, that is essentially a gamma ray. They can cause mucho damage. I forgot the word for much in English. So gamma rays are on the other end of the spectrum from the really, really long radio waves that we saw. And we're seeing, as you know, the wavelengths get shorter, the energy becomes greater, and the more it can tell us about aspects in space. So if something is emitting gamma rays rather than radio waves, there's a lot more energy, which is cool to know. So I hope if you have any questions about these different types of light and how are they useful, or what else you want to know, please reach out to me. You'll have contact information on the handouts, and also if you have any questions about the assignment, please feel free to email me at hbuckner@fairbanksmuseum.org. It has been an absolute pleasure to be teaching this class series. It has been a complete joy, and I am glad to share the world of physics and astronomy with you all. So thank you so much.